Hello, everyone. Today I am very pleased to present our work titled WavePolyp, Video Polyp Segmentation via Hierarchical Wavelet-Based Feature Aggregation and Interframe Divergence Perception. This slide shows the major challenges of video polyp segmentation. The first challenge is significant interframe divergence. In colonoscopy videos, the polyp may change rapidly across adjacent frames in terms of position, shape, and size. This makes stable tracking and segmentation very difficult. The second challenge is high camouflage. Polyps often look very similar to the surrounding mucosa in color, texture, and appearance. As a result, the boundary between foreground and background can be. Now I will introduce the overall pipeline of WavePolyp, and at the same time briefly explain the ideas of our two key modules, HWFA and IDP. Starting from the left side of the figure. The input is a video clip with T-frames. Inspired by ZoomNext, we generate two auxiliary scales, namely 0.75 times and 1.25 times, in addition to the original 1.0 times scale. The intuition is that different zoom levels provide complementary visual information, just like how physicians zoom in and out during inspection. These three scale clips are then fed into a shared feature extractor, followed by a scale merging network, to produce unified multi-level features. After that, the network branches into two important parts. The first one is HWFA, which is designed to solve the problem of high camouflage. In colonoscopy videos, the polyp often looks very similar to the surrounding mucosa, so conventional spatial features are not discriminative enough. To address this, HWFA decomposes the multi-level features into high-frequency and low-frequency components using discrete wavelet transform. The high-frequency branch mainly focuses on subtle details such as edges and textures, while the low-frequency branch captures more global information, such as color, illumination, and lesion structure. These two types of frequency cues are then enhanced separately and hierarchically aggregated across levels. So the network can recover both fine boundary details and holistic lesion structure more effectively. Concretely, inside HWFA, the decomposed features are refined by dedicated enhancement units, and then progressively fused from high level to low level through an ascending frequency-guided aggregation process. In the end, the aggregated high-frequency output is injected into the shallow feature to strengthen detailed representation, while the aggregated low-frequency output is fused into the deeper feature to preserve global semantic context. So the core idea of HWFA is: use frequency domain decomposition and hierarchical aggregation to make the model see camouflaged polyps more clearly within each frame. The second key part is IDP, which is designed to handle interframe divergence. In video polyp segmentation, adjacent frames may vary a lot in position, size, shape, and boundary. If we only rely on intraframe features, the model may produce unstable masks or temporal flickering. Therefore, in the decoder, we introduce IDP blocks to explicitly model the differences between consecutive frames. More specifically, given the current feature, IDP first constructs temporal representations and performs a temporal shift operation. Then it computes the difference between shifted and original features to obtain what we call interframe divergence. After that, a temporal attention mechanism is applied along the time dimension to highlight the most meaningful temporal changes, rather than all changes equally. Finally, the extracted temporal divergence cues are diffused and added back to the original visual features. In this way, IDP helps the network focus on true motion-related changes of the polyp, instead of being distracted by noise or deformation artifacts. Finally, in the decoder, these IDP-enhanced features are processed in a coarse-to-fine manner, starting from the deepest feature. Each stage applies IDP, upsamples the result, and fuses it with the next finer scale feature, until the final prediction is generated by the Polyp predictor. So to summarize this slide in one sentence, WavePolyp first improves intraframe discriminative representation through HWFA, and then improves interframe temporal consistency through IDP, so that the model can segment camouflaged polyps more accurately and track them more stably across video frames.
This slide shows the internal design of HWFA, which consists of three components: HFC, LFC, and AFA. First, HFC, or the High Frequency Calculation Unit, is designed to enhance texture-rich and boundary-sensitive regions. It strengthens the subtle local details that are useful for distinguishing the polyp from its surrounding tissue. Second, LFC, or the Low Frequency Calculation Unit, focuses on global structural information, since low-frequency features may also contain redundant background information. LFC uses a dedicated normalization strategy to suppress interference and emphasize cleaner global lesion cues. Third, AFA, or the Ascending Frequency Guided Aggregation Unit, is used to hierarchically fuse frequency information across different levels. This part is important because directly concatenating enhanced features from multiple scales may introduce misalignment and noise. AFA performs a more adaptive and guided aggregation, which helps preserve both semantic consistency and spatial detail. So overall, HWFA is not only a decomposition module. It is a frequency-aware enhancement and aggregation mechanism. This slide introduces the datasets used in our experiments. We evaluate our method on two public video polyp segmentation datasets. The first one is SunSeg, which is a large benchmark dataset for VPS. It contains a training set, as well as two test subsets, SunSeg Easy and SunSeg Hard. The hard subset is especially useful for evaluating robustness under more difficult cases. The second one is CVC 612, which contains 612 frames from 31 colonoscopy clips. For all experiments, we resize each frame to 352 by 352. We report 4 standard evaluation metrics, including DICE, structure measure S-alpha, enhanced alignment measure E-phi, and weighted F measure. These metrics provide a comprehensive evaluation of both overlap quality and structural consistency. This slide shows qualitative comparisons with other state-of-the-art methods. There are 2 key observations here. First, in highly camouflaged scenes, many existing methods either miss part of the lesion or produce blurry and inaccurate boundaries. In contrast, our method provides clearer contours and more complete segmentation masks. Second, under large interframe changes, some methods show unstable predictions, such as shape drift or inconsistent region estimation. Our method remains more stable and better aligned with the ground truth. These results are consistent with our design. HWFA improves the discriminative representation within each frame, while IDP improves temporal consistency across adjacent frames. This slide presents the quantitative comparison with state-of-the-art methods on SunSeg Easy, SunSeg Hard, and CVC 612. As shown in the table, our method achieves the best overall performance across these datasets. For example, on SunSeg Easy, our method achieves a DICE score of 88.96. On the more challenging SunSeg Hard subset, we obtain a DICE score of 87.55. On CVC 612, our DICE reaches 94.36. Our method also performs very strongly on the other metrics, including S-alpha, E-phi, and weighted F-measure. Another point worth mentioning is that some competitive methods, such as VP-SAM, rely on additional prompts, such as point guidance for each frame. This is less practical in real clinical settings. In contrast, our method does not require such extra manual interaction, which makes it more suitable for realistic deployment. This slide shows the ablation study results. First, if we remove either HWFA or IDP, the performance drops. This indicates that both components are effective and necessary. Second, when HWFA and IDP are used individually, they each bring performance gains. But when they are combined, the improvement becomes larger. This demonstrates that the two modules are complementary. HWFA improves intra-frame discrimination, while IDP improves inter-frame consistency. We also study the internal design of HWFA. The results show that HFC, LFC, and especially AFA all contribute to the final performance. In fact, removing AFA can even make the performance worse than the baseline. Because strong frequency enhancement without adaptive aggregation may amplify spatial misalignment across scales. Similarly, for IDP, each component, including temporal shift, divergence attention, and divergence diffusion, contributes to the final performance. This slide provides visual evidence for the ablation study. On the left, we compare the prediction results when removing different modules. Without HWFA, the model becomes weaker at handling highly camouflaged polyps and the lesion boundaries are less clear. Without IDP, the model becomes less stable under temporal changes, and the segmentation may become discontinuous or inaccurate across frames. When both modules are present, the prediction is more complete, more precise, and more stable. On the right, the T-SNE visualization further supports this observation. After introducing HWFA, the foreground and background features become more separable in the feature space. This means HWFA does not just improve the visual appearance of the masks. It actually improves the discriminative structure of the learned representation. This slide visualizes what HWFA learns from the frequency domain. From left to right, we show the original frame, the prediction mask, the high-frequency feature, and the low-frequency feature. We can see that the high-frequency feature mainly focuses on boundaries, textures, and fine local details. This makes it very suitable for refining shallow features and preserving subtle lesion cues. In contrast, the low-frequency feature mainly captures the overall lesion body and global structural context. This is useful for enhancing deeper features and preserving global semantic understanding. So, these visualizations clearly show that HWFA successfully disentangles and aggregates complementary information, high-frequency cues for detail, and low-frequency cues for structure. To conclude, we propose WavePolyp, a new framework for video polyp segmentation. The key idea is to improve segmentation from both the intra-frame and inter-frame perspectives. On the one hand, HWFA enhances intra-frame discriminative features through hierarchical frequency domain modeling, which helps the model better segment highly camouflaged polyps. On the other hand, IDP captures temporal divergence across adjacent frames, which improves tracking stability and reduces temporal inconsistency. Extensive experiments on SunSeg and CVC 612 demonstrate that our method achieves state-of-the-art performance while maintaining a strong balance between accuracy and efficiency. However, there are still some limitations. As shown by the failure cases, the model may still struggle under extremely difficult conditions, such as missing details, distorted lighting or focus, and overlapping intestinal walls. These challenging cases provide directions for future work. This slide demonstrates the effect of IDP on temporal stability. Here we show continuous frames from a video sequence. The second row corresponds to the model without IDP, and the third row corresponds to our full model. Without IDP, the segmentation masks show noticeable flickering and unstable boundaries across time. In contrast, with IDP, the predictions are much smoother and more temporally consistent. This result matches the purpose of the IDP design. Instead of simply fusing temporal information, IDP explicitly models interframe divergence, so that the network can better distinguish meaningful temporal changes from noise and improve continuous tracking of the polyp target. Thank you for your listening. If you have any questions, feel free to contact us.